Okay, in this lecture we're going to finish our section 6.2 material on solving initial value problems by using a Laplace transform. Now in the first part of this section, we saw a property that we call the lifting property of the Laplace transform, which allows us to rewrite the Laplace transform of a derivative or higher order derivatives of a function in terms of the Laplace transform of the original function. And we also talked about the idea of an inverse Laplace transform. So these concepts are going to be very important for the last part of this section when we start looking at solving these initial value problems. So in this first example, we are asked to use the Laplace transform to solve the given initial value problem. And we have here a second-order linear homogeneous equation with constant coefficients. So one way that we could solve this initial value problem would be to look for solutions of exponential form, y equals e to the rt, and then obtain a characteristic equation. However, here we are given the direction use the Laplace transform to solve. So our first step in using a Laplace transform to solve an initial value problem is to take the Laplace transform of our equation. And because the transform is linear on the left-hand side of this equation, I can take the Laplace transform term by term, giving me the Laplace of y double prime plus 3 times the Laplace of y prime plus 2 times the transform of y. That's equal to the Laplace transform of 0, which is just 0. And once I take the Laplace transform of both sides, on the left-hand side, where I have these expressions involving the Laplace transform of the first or second derivative, I'm going to use my lifting property of the Laplace transform. So the Laplace transform of y double prime is given by s squared times the Laplace transform of y, which we denote as capital Y of s, minus s times y 0 minus y prime at time 0. And then we are adding to that 3 times the Laplace transform of y prime. So again, applying the lifting property, the Laplace of y prime is given by s times the Laplace transform of y, which we call capital Y of s, minus y of 0. And then I'm adding on the end 2 times the Laplace transform of y. And this was equal to the Laplace transform of 0, which is just 0. So after I apply this lifting property, I have expressions involving y naught or y prime at time 0. And we're given these values as our initial conditions. Y of 0 was 1, y prime of 0 is 0. So applying these initial conditions, I have s squared times the Laplace transform of y minus 1s minus 0 plus 3 times s times the transform of y minus 1 plus 2 times the Laplace transform of y, and this is equal to 0. So on the left-hand side, if I expand and group like terms, let me start by grouping all the terms involving capital Y. So on the left-hand side, I'm going to have s squared plus 3s plus 2 all times capital Y. And then I've got remaining values of minus s minus 3, and this is equal to 0. So from here, I can solve for capital Y by first multiplying both, or first adding s plus 3 to both sides, and then dividing through by the coefficient of capital Y, which was s squared plus 3s plus 2. And once I have solved for capital Y, which is the Laplace transform of my solution, little y of t, I want to find my inverse transform to get my solution. So we need to find the inverse transform of this capital Y expression. And if I look at my denominator here, I see that my denominator could be factored down to linear terms. So I have s plus 3 over s plus 1 times s plus 2. And since my denominator is a product of terms, I need to make use of partial fractions to rewrite this product in terms of a linear combination of smaller terms. So using partial fractions here, I'm going to rewrite s plus 3 over s plus 1 times s plus 2 as some constant a over s plus 1 plus b over s plus 2. And so to solve for a and b, I could multiply both sides by the common denominator, s plus 1 times s plus 2, giving me s plus 3 is equal to a times s plus 2 plus b times s plus 1. And there's a number of ways I could go about solving for a and b here. One simple way would be to substitute particular values of s into this equation. If I wanted to solve for a, I could substitute s equals -1 into the equation, which would result in 2 is equal to a. And if I want to solve for b, I could substitute s equals -2 into the equation, in which case I would have 1 is equal to negative b, implying that b is -1. So taking these expressions and substituting back into my partial fraction decomposition for capital Y, I have a, which is 2 over s plus 1, plus b, which is -1 over s plus 2. And so for my solution of this initial value problem, little y of t, I want to find the inverse transform of capital Y. And so I could find my inverse transform term by term as twice the inverse transform of 1 over s plus 1 minus the inverse transform of 1 over s plus 2. So making use of property number 2 from our table of Laplace transforms, we find that this inverse transform is 2e to the -1t minus e to the -2t. And if you were to solve this initial value problem using a characteristic polynomial, you would find the same result. So here this method is consistent with what we would obtain by applying some other method. So let's take a look at another example. Here we are asked to use the Laplace transform to solve this initial value problem. We have here a fourth order linear homogeneous equation with constant coefficients. So again, we could make use of a characteristic polynomial, but we're told to use the Laplace transform here. So our first step is to take the Laplace transform of our equation. So on the left-hand side, I can take the transform term by term. And on the right-hand side, I have the Laplace transform of 0, which is just 0. And once I take my transform, I then want to rewrite the Laplace transform of any derivatives by using the lifting property. So for the Laplace transform of the fourth derivative of y, I have s to the fourth times the Laplace transform of y minus s cubed times y of 0 minus s squared times y prime of 0 minus s y double prime of 0 minus y triple prime of 0. And then I am subtracting the Laplace transform of y, which we denote as capital Y. And this is equal to the transform of 0, which is 0. And again, once I apply this lifting property, I have expressions involving the initial value of y or its derivatives. So I'm going to substitute my initial conditions into these expressions. And we have on the left-hand side s to the fourth capital Y of s minus s cubed times 1 minus s squared times 0 minus s times 1 minus 0 minus my Laplace transform of y, and this has to be 0. So from here, I want to try to solve for capital Y of s, the Laplace transform of my solution. So let me start by grouping the capital Y terms on the left-hand side. We would have s to the fourth minus 1 times capital Y minus s cubed minus s is equal to 0. And so solving for y, we would first add s cubed plus s to both sides, and then divide through by the coefficient of capital Y, which was s to the fourth minus 1. Now from here, I want to find my inverse transform. And so looking at this expression, I see that my denominator, s to the fourth minus 1, could be factored as s squared plus 1 times s squared minus 1. And my numerator, if I factor out an s, leaves me with s squared plus 1. And this then allows me to cancel a factor of s squared plus 1, leaving me with capital Y is s over s squared minus 1. And so using our Laplace table, we can then find our solution, little y of t, by taking the inverse transform of capital Y, which reduced to s over s squared minus 1. And this inverse transform is hyperbolic cosine of 1t. So we obtain our solution here. And of course, another way that we could have solved this differential equation would be to use a characteristic equation or characteristic polynomial. And for this example, that characteristic equation approach is more difficult than this Laplace transform method. However, we would get the same answer in the end using either method. So let's look at another example. Here we're again told to use the Laplace transform to solve this initial value problem. And we have here a second order linear non-homogeneous equation with constant coefficients. So we could make use of our earlier approaches where we solve the homogeneous equation first using a characteristic equation and then use undetermined coefficients to find a particular solution. However, here we're told to use the Laplace transform. So let's take a look at this one. Our first step would be to take the Laplace transform on both sides of my equation. And since the transform is linear, on this left-hand side, I can take the transform term by term. And for this one, since I have a non-homogeneous equation, on my right-hand side, I'm taking the transform of e to the negative t. So once I've taken the transform of my equation, let's apply the lifting property to rewrite the transform of my derivatives on the left-hand side. And for the Laplace transform of y double prime, I have s squared times the transform of y minus s times y naught minus y prime of 0. Then I'm subtracting 2 times the Laplace transform of y prime, which would be s times the Laplace transform of y minus y naught. And then I'm adding 2 times the Laplace transform of y. And this is equal to the Laplace transform of e to the negative t. So using my Laplace table, the transform of that function would be 1 over s minus negative 1, or 1 over s plus 1. So our next step is to again apply our initial conditions for y of 0 and y prime of 0. We see that y naught is 0, so these two terms will disappear, and our y prime value is 1. So on the left-hand side, if I group all of the capital Y terms together, I have s squared minus 2s plus 2 times y, and then minus y prime of 0, which was 1. And this is equal to 1 over s plus 1. So solving for capital Y, I could add 1 to both sides and then divide through by my coefficient for capital Y, which leaves me with the following. So here, my capital Y expression is the sum of these two rational functions. And from here, I need to try to find my inverse transform. So when I look at this second term, I see that my denominator is a product of two factors, s plus 1, and this irreducible quadratic, which can't be factored down to linear terms. So I know I'm going to need to use a partial fraction decomposition to rewrite that product as a linear combination of smaller, simpler terms. And since capital Y consists of two parts here, the sum of these two fractions, I think what I might do first is rewrite these as a single fraction and then perform a decomposition on that single rational function. So here my capital Y expression, if I rewrite it as a single function by using a common denominator of s plus 1 times s squared minus 2s plus 2, I would have s plus 1 plus 1, so s plus 2 divided by this product, s plus 1 times s squared minus 2s plus 2. And so let's look for a partial fraction decomposition of this function, which would have the form a over my linear factor, s plus 1, plus bs plus c, that is a linear function, divided by the irreducible quadratic. So to solve for a, b, and c, I could multiply both sides of this equation by my common denominator, giving me s plus 2 is equal to a times s squared minus 2s plus 2 plus bs plus c times s plus 1. And so on the right-hand side, if I expand and group like terms, let's see what we have. So I would have a coefficient of s squared given by a plus b, s squared. Then for my coefficient of s to the first, I would have a negative 2a plus b plus c, all times s. And then my constant coefficient would be 2a plus c. So equating these coefficients, I find that a plus b must be 0, negative 2a plus b plus c must be 1, and 2a plus c must be equal to 2. So there's a number of ways I can solve for a, b, and c. I think what I would do here is to solve my first equation for b in terms of a, and solve my last equation for c in terms of a, and then substitute both of these expressions into my second equation, which would give me negative 2a plus b, which is negative a, plus c, which is 2 minus 2a, and this has to equal to 1. So it follows then that 5a is equal to 1, and therefore a is 1/5. So it then follows that b is negative 1/5, and c is 2 minus 2 times a, So that would be 2 minus 2/5, which leaves me with 8/5. So substituting these expressions back into our capital Y expression, we have a partial fraction decomposition of A, which is 1/5 over s plus 1, or 1/5 times 1 over s plus 1, plus bs plus c. And since b and c both involve a factor of 1/5, if I factor out a negative 1/5 from those terms, I would have a positive s minus 8 over my s squared minus 2s plus 2. So now that I have my partial fraction decomposition, I want to find the inverse transform of each of these terms. And the first term is pretty simple. We can find our inverse transform directly. It would be 1/5 e to the negative t. However, this second term has a denominator which is an irreducible quadratic, but it's not a sum or difference of squares. So we've seen for those types of functions, we need to complete the square for the quadratic denominator to make this look like one of the properties from my Laplace table. So let's complete the square in that second term. So we have here 1/5 of 1 over s plus 1 minus 1/5 of, completing the square in our denominator, I would have s minus 1 quantity squared plus 1. And for my numerator, after I have completed the square, the factor that I have, s minus 8, well, to use the properties from my Laplace table, I want to rewrite this in terms of s minus 1, the factor that's being squared in that denominator. So here, this s minus 8 expression, I could rewrite as s minus 1 minus 7. And if I split up this second part of my capital Y expression, I have capital Y is 1/5 of 1 over s plus 1 minus 1/5 of s minus 1 over s minus 1 squared plus 1, and then a plus 7/5 of 1 over s minus 1 squared plus 1. And so finally, I have something that I can find my inverse transform of directly from the properties in my Laplace table. So here, my solution, little y, which would be the inverse transform of capital Y, is 1/5 of e to the negative t minus 1/5 of e to the positive t times cosine of 1t plus 7/5 times e to the 1t times sine of 1t. And here, if we were to go through the process of solving the homogeneous equation using a characteristic polynomial, and finding a particular solution using the method of undetermined coefficients, I would end up with the same answer that we found here by using this method of Laplace transform.